A 200-meter water drop inside a sealed concrete shaft can produce enough electricity to power a city for a few seconds. That sounds almost impossible until you follow the physics. Hydroelectric dams turn falling water into electricity by using gravity, pressure, and spinning machinery. The idea is old, but the engineering is still extraordinary. There are roughly 40,000 large hydroelectric dams operating around the world, and together they generate about 16% of global electricity. In countries like Norway, Brazil, and Canada, the share is far higher. These are not relics. Many of the largest dams were built in the last half-century, and they all work on the same basic principle: water falls, a turbine spins, and electricity flows. The process begins in the reservoir, the artificial lake behind the dam. The reservoir stores potential energy in the form of water held at elevation. The greater the vertical distance between the water surface and the turbines below, the more pressure is available to drive power production. Engineers call this distance the head. Head is the starting point for every other design choice. Water does not simply spill into the turbines. It travels through a penstock, a massive steel pipe that can be several meters wide and is built to handle enormous pressure. As the water falls through it, velocity rises sharply. By the time it reaches a 200-meter head, it may be moving at around 60 meters per second. That high-speed flow is aimed directly at the turbine. Between the penstock and the turbine sits the wicket gate, a ring of adjustable steel blades that acts as the dam's throttle. Open the gates wider and more water hits the turbine. Close them and output drops. Operators use the wicket gates to match power production to grid demand. The response is fast, which is one reason hydroelectricity is so valuable. Solar disappears at sunset. Wind calms down. Hydroelectric stations can move from idle to full output in under 2 minutes. Most large stations use Francis turbines, a design developed in the 1840s and still the standard for medium and high head applications. Water enters from the outside, moves inward through curved runner blades, and exits downward through the center. The blade geometry is tuned to extract as much kinetic energy as possible. A single runner can weigh hundreds of tons and spin at 150 revolutions per minute. Modern Francis turbines can convert more than 90% of the water's energy into rotation. Below the turbine, the water passes through a draft tube, which slows it down and recovers a little more energy through pressure effects. Then it returns to the tail race and rejoins the river downstream. The water is not consumed, it was simply moved downhill, gave up its stored energy, and returned to the river system. That is why hydroelectricity is renewable. The water cycle refills the reservoir. Above the turbine hall sits the generator hall, a much cleaner and quieter space. The turbine shaft drives a massive rotor wound with copper wire and surrounded by electromagnets. As the rotor spins, the copper moves through the magnetic field and electricity is produced. That is Faraday's law of electromagnetic induction in industrial form. The scale is huge, but the principle is the same as a simple laboratory experiment from 1831. The generator produces alternating current at 50 or 60 cycles per second, depending on the grid. Its rotational speed is locked to that frequency by design. A governor automatically adjusts the wicket gates to keep the rotor speed constant as electrical demand changes. If the grid load changes, the gate opening changes. If the frequency drifts, the turbine is corrected. The machine is built to stay in sync with the grid. Once generated, the electricity passes through a step-up transformer. The generator may produce around 11,000 to 20,000 volts, but transmission requires much higher voltage to reduce resistive losses. The transformer raises the voltage to hundreds of thousands of volts so the electricity can move efficiently over long distances. Later, step-down transformers reduce it again before it reaches homes and businesses. Large stations are modular. A plant like the Three Gorges Dam in China has dozens of main turbine generator units. Itaipu on the Brazil-Paraguay border has 20. Each unit can be maintained independently, which gives the plant flexibility and redundancy. If one bearing overheats, that unit can be isolated while the others keep producing. The grid barely notices. The dam structure itself is a separate engineering challenge. Gravity dams, like Hoover, rely on sheer mass to resist water pressure. They are thick concrete wedges, wider at the base than at the top. Arch dams are thin curved walls that transfer force into the canyon walls, but they require strong geology. Earth-fill and rock-filled dams are more common still. They are built from compacted earth and rock with an impervious core, often clay, to stop seepage. They are cheaper than concrete dams and can be built where high-quality rock is scarce. Choosing among those dam types is a matter of geology, cost, and river shape. A narrow, rocky gorge favors an arch dam. A broad valley with weaker sidewalls usually needs a gravity or embankment design. Engineers study foundations, seismic risk, flood history, and sediment load before deciding what kind of structure can survive for decades without shifting or cracking. Every dam must also manage floods. The spillway is the safety valve. If the reservoir rises too high, water is released through the spillway to prevent overtopping or structural failure. Spillways can be overflow crests, concrete chutes, tunnels, or free jet systems that launch water into the air before dropping it into a dissipation basin. A dam that cannot safely release floodwater is a dam waiting for disaster. The 1976 failure of the Teton Dam in Idaho remains a warning. It was an earth-filled structure that failed during initial filling when water began seeping through its foundation rock. Engineers noticed the seepage but did not stop the reservoir from rising. The seepage worsened, the face cracked, and the dam collapsed. The flood devastated the Snake River Valley and changed dam safety regulation around the world. Modern projects now require failure mode analysis and much more rigorous monitoring. Today, large dams are instrumented with dozens or hundreds of sensors. Piezometers measure pore water pressure inside the structure. Extensometers track tiny deformations. Seismographs watch for earthquakes. GPS receivers monitor movement at the crest. The dam is effectively a machine that reports on its own health in real time. One of the least visible but most important parts of the system is the intake. This is where water first enters the penstock. The intake is usually submerged, fitted with trash racks to block debris and equipped with gates that can shut off flow for maintenance. Because the pressure is so high, a bad seal can produce a jet powerful enough to cut steel. The engineering tolerance at this point is not optional. Sediment is another long-term problem. Rivers carry silt and sand, which settle in the reservoir and slowly reduce storage capacity. In some places, sedimentation removes about 1% of capacity per year. Some dams flush sediment through low-level outlets, but that only works in certain river systems. There is no perfect fix. Fish passage is also a major issue. Migratory fish like salmon and steelhead need to move upstream to spawn, but a dam wall is a barrier. Fish ladders help some species climb around the obstacle, but downstream migration is harder. Juvenile fish can be pulled through turbines, suffering pressure injuries or dying from blade strikes. Engineers now use screens, bypass channels, and even trucking systems to move fish past dams. The John Day Dam on the Columbia River has transported millions of juvenile salmon by barge. The downstream environment changes too. Deep reservoir outlets release colder water with less oxygen than a natural river would have. That alters algae, invertebrates, and spawning cycles for hundreds of kilometers. Environmental flows are now used to restore some seasonal variation, but a dam never leaves the river exactly as it found it. Pumped storage hydro turns the dam concept upside down. When electricity is cheap or abundant, water is pumped uphill into an upper reservoir. When demand rises, the water is released back through turbines and the plant generates electricity again. It is grid-scale energy storage with round-trip efficiency around 70 to 85%. The Bath County Pumped Storage Station in Virginia is the largest of its kind in the United States and one of the largest energy storage devices ever built. In practical terms, hydro is both a power source and a battery. The reservoir stores energy in the form of elevation. The turbines release it as electricity when the grid needs it. That flexibility is why utilities value hydro so highly. The environmental debate around large dams is real. Some projects flood huge areas and displace communities, others destroy forests or alter entire river systems. Tropical reservoirs can emit methane as drowned vegetation decomposes. In some cases, those emissions can rival fossil fuel plants in early years. Climate change adds another layer. Drought and shifting rainfall patterns can reduce output and strain assumptions built into older dams. The Kariba Dam on the Zambia-Zimbabwe border is one example. Built on mid-20th century flow data, it has faced serious output reductions during drought years because the river now behaves differently than the designers expected. Hydrology is changing, and dams designed for old climate patterns are being forced to adapt. Removing dams is now a serious engineering field as well. In the United States, thousands of smaller dams have outlived their purpose or reached the end of their design life. When the Elwha and Glines Canyon dams were removed in Washington state, salmon returned to river reaches that had been blocked for more than a century. River restoration does not turn time back completely, but it can recover far faster than many people expect. The technology keeps evolving too. Variable speed generators, improved Kaplan turbines, tidal systems, and small run-of-river microhydro installations all extend the basic idea into new settings. The core machine is still the same. Water moves, a shaft spins, a magnet turns inside copper, and electricity comes out. That basic system is more than 150 years old and still among the most efficient energy converters ever built. A hydroelectric dam is ultimately a translation device. It turns the slow accumulation of water across a watershed into electricity at the moment someone needs it. Rain falls on mountains, snow melt runs into rivers, water collects behind a dam, and the stored energy is released on demand. No other large-scale system performs that translation with such reliability. That does not make dams simple or innocent. They reshape rivers, displace communities, and store consequences as well as energy. But they also provide low-carbon power, grid stability, and storage that no other technology has yet matched at comparable scale. The debate over how many dams to build, which to retire, and how to manage the ones already here is really a debate about the future of the grid. The physics is settled. Falling water can be turned into electricity with extraordinary efficiency. The hard question is what we are willing to change in the river to get that power, and what we are willing to restore when the dam is no longer worth keeping. Hydropower also has a quieter role in modern grids. It balances volatility. When demand spikes unexpectedly, hydro can ramp quickly enough to cover gaps while slower generators respond. That means the dam is not only a source of kilowatt hours, it is a stabilizer that helps a whole electrical network avoid blackouts and frequency swings. Because of that flexibility, utilities often think of hydro plants as both generation and insurance. They may not be the cheapest source in every hour, but they are among the most adaptable. In systems with lots of wind and solar, that adaptability becomes more valuable, not less, because the grid needs something that can respond instantly when clouds pass or wind drops. The long-term challenge is ownership of the landscape itself. A dam is not just a machine. It is a claim on a river valley, a floodplain, a fisheries system, and often a community. Once built, it can last for generations, which means the original decision outlives the people who made it. That is why debates about dam replacement or removal tend to become arguments about memory, justice, and the future all at once. The great irony of hydropower is that it looks static but behaves dynamically. The wall seems immovable, yet the real action is in the moving water, the adjustable gates, the dispatch decisions, and the seasonal rhythm of rainfall and snowmelt. A dam is a fixed structure built to manage something that is constantly changing. That is what makes hydropower one of the most enduring industrial inventions ever built. It takes gravity, the oldest force in everyday life, and turns it into a controllable, grid-scale energy source. The machines are massive, the controls are delicate, and the consequences of getting it wrong are severe. But when it works with remarkable elegance. So a 200-meter water drop is not just a dramatic image, it is the heart of a system that links mountain hydrology, turbine metallurgy, transmission engineering, ecology, and electrical demand into one immense machine. The water is not consumed, it is borrowed, converted, and returned. And that is why hydroelectric dams still matter. They turn a river into power without breaking the basic rule that the river must keep going. Designing that system begins long before concrete is poured. Engineers model seasonal flows, sediment loads, flood recurrence intervals, and downstream water rights. A dam that looks ideal on paper can fail in practice if the river brings more silt than expected, or if the watershed's rainfall pattern changes after construction. That is why hydropower projects often include decades of hydrology studies and environmental review before a single gate is installed. Even after a plant is built, the operating strategy is never fixed. Reservoir managers decide when to store water for summer cooling demand, when to release it for peak electricity prices, and when to hold it back for flood control. A wet year and a dry year can produce very different outputs from the same installation, so the dam is always being managed against the weather as well as the grid.